Welcome to today's program, Permeable Design Pro software program for structural and hydrologic design. Please be aware that this webinar and its recording are copyright of the Interlocking Concrete Pavement Institute and shall not be reproduced, altered, supplemented, disseminated, or transmitted in any form or by any means. Today we have David Hein presenting with David Smith as a guest panelist. It is my great pleasure to introduce you to our presenter today, Mr. David Hein. Mr. Hein recently retired from Applied Research Associates, Inc., ARA, in Toronto, Ontario. He has over 35 years of experience in the design, evaluation, and management of pavement infrastructure. He has been extensively involved in the structural and hydrologic design of permeable pavements. He has authored 18 papers and completed over 60 workshops and webinars on the subject. He is the chair of the American Society of Civil Engineers Permeable Pavement Committee to publish the standard ASCE 68-18 on permeable pavements. He is a technical reviewer for an ASCE ebook on permeable pavements and has completed design, construction, and maintenance guidelines for many agencies in Canada and the US. Dave, thanks so much for joining us. The floor is yours.
Thank you very much. Much appreciated. And my colleague Dave Smith is online with us as well, and I've asked him to just jump in and add some additional comments or insight as we go through this. So I'm going to spend the next hour or so talking about permeable interlocking concrete pavements, and particularly the Permeable Design Pro software. For those of you who may not be familiar with permeable pavements, this is basically what they look like. We take an existing pavement that has typically got dense graded aggregates, and we change it so we allow, instead of water to run off the pavement, we allow water to permeate into the pavement surface itself. And then the layers below them are all also permeable. We basically use large stones that have very few small particles in them to allow you to both store and to transfer water from place to place. So it goes through the surface, goes through the bedding layer, the base layer, the subbase layer. Subbase layer we usually call a reservoir layer, so it's a location where we can store water, and that water volume is typically 35 or 40% of the volume of that particular layer. The design of permeable pavements is very similar to existing dense graded pavements, but we have an additional component, the hydrologic side. On the left side here, you see a basic flowchart of the structural analysis process that we go through. Pavements are designed for the traffic that they have on them, be it vehicular, pedestrian, whatever. And we look at materials in that pavement structure, such as the subgrade, how strong it is, exactly like we would a normal pavement. We also then look at the permeability of that lower layer. So the subgrade layer, the earth that we build it on, we would love to be able to get water into that layer. And depending on the type of layer, it will be able to take water at different time periods. So you look at something like the East Coast and Outer Banks of North Carolina, you got very sandy soils, and those are very open, and so water can permeate into them very easily. The majority of the US and Canada in the middle is basically silty clays and clay silts and till materials, much less permeability, but they still will take water. And so we do a few different things to be able to get more water into the ground with those kind of soils. We look at the traffic, how many easels, the equivalent single axle loads that we have using the pavement surface. Talk a little bit about that more as we move through here. And then ultimately, we determine how much strength do we need to accommodate that design traffic over time, and we design the pavements for that. The other component of this is the hydrologic side, which is on the right-hand side of the graphic you see. And so we need to know about water. So where's the water coming from? Obviously, it's falling from the sky and getting on top of our pavement, but we also have water potentially coming from the area surrounding the pavement. If you look outside your window and you see the road in front of your house, the road is probably the lowest point that you see. And so the water will go to it. And so in a conventional pavement, we put in catch basins or ditches and things like that, and pipes underground to accommodate the water. In a permeable pavement, that water may flow off your grass or your driveway or the roof of your house or a building beside you, and it will also go to that permeable pavement. So we have to account for that water that we also get from the contributing area, we call it. So we look at the storms that we have. We look at what's the intensity of that storm, how much water comes to the pavement, how fast does it get there, not just what falls on it, what comes off of the buildings or on the front lawn or the parking area or the cornfield or the park. And we combine all the water that comes to the pavement, and then we have to ensure that it has the capacity to first infiltrate it, get it into the ground, into the pavement structure, and then we find out where it goes. So we figure out how much water goes into the ground, how much water will not go into the ground or will start building up. Typically in our storm events that we have in North America, it starts to rain and it gets much higher intensity in the middle of the storm, and then it starts to peter off. And so we basically model it through all that period. If a pavement is just thick enough to handle the traffic and just thick enough to handle the design storm that you want to do, then you've got a balanced design. And so ultimately, if you don't, you may have to have a thicker pavement because maybe I'm building a parking lot to handle only cars in Houston, where a 100-year storm is going to be 15 or 16 inches of rain. And so it's going to have to be probably thicker to accommodate the hydrology, the water, than it is to be handling the cars that are there. So, but ideally, if we can make a balance between the two, then we basically win and you get the most cost-effective pavement structure. So we're going to talk about Permeable Design Pro. This is a piece of software that was developed more than 10 years ago now, that was designed to help people design permeable pavements, and both structural and hydrological side. It is available online for purchase. I don't recall exactly what the dollar value is, but it's not substantial. Also, it's free upon request from an ICPI member. Within that piece of software, we have tons of rainfall information available for Canada, the United States. Also, New Zealand was added to that recently, and we're looking at other places as well. And so, or if you don't, we don't have the rainfall data that's available within the program itself, you can get it and enter it yourself. So if you're in South Africa or Europe or wherever, you can actually enter the storm information manually. It does structural design. So we're going to talk about two methods of structural design today, and it incorporates both. Works both in metric and conventional US units. We take care of underground piping and sizes and things like that. We provide outputs in volumes and flows of water at 6-minute intervals. Literally, you can copy and paste it and put it into a spreadsheet and do your own calculations if you want. Does things like provides runoff coefficients and curve numbers that are a composite of whatever you're designing, the permeable pavement itself and the surrounding areas. Also, based on what you design in the software, it will produce a CAD drawing. And so you can simply click on the button, which I'll show you. It'll produce a CAD drawing. You can then take that, edit it, modify it, do whatever you like. And then there's tons of sensitivity analysis. And so we'll go through that in a few minutes. So the history, I said this program has been around for 10 years. A couple of years before that, a lot of testing was done on it. It's based on ICPI's 4th edition of the Permeable Pavement Manual. It has been updated to include ASCE now as well. Structural design does the AASHTO 93 design. AASHTO is the American Association of State Highway and Transportation Officials. Very common pavement design procedure that is being used throughout North America, certainly. And we'll talk about the ASCE method a little bit later. It's more of a mechanistic design. The program has been upgraded several times along the way, and most recent one actually happened this week. So any of you who have this software already and you click on it, it's going to tell you, and you're connected to the internet, it's going to say there's an update available for you. And I'll show you some of the new features that are in there in this presentation as well. All right, so this is the design methods. There are hard copy documents that are available from ICPI and or the American Society of Civil Engineers. And early, you heard Michael mention I chaired a Permeable Pavement Committee, and so that's ASCE 6818. The standard was developed by a group of people from Canada and the US, pretty much evenly balanced on both sides. And we sat together for almost 4 years, I would say, and basically did the best we could at producing the best design process that we had for permeable pavements, permeable interlocking concrete pavements in particular. And so this has now all been reflected in the software you're seeing now as well. The documents, you can click on the software when you load it, basically, and it'll come up and tell you about them and where you can get them and stuff like that. This is what the opening screen looks like when you turn it on. All right, so ASCE 6818, the part that's included in here was developed. So as we were working on this standard at ASCE, industry and the folks in the room basically suggest, bottom line is that AASHTO 93 is an old design procedure based on the original construction of the interstate highway system. And so the most of the world, including Canada and the United States, are moving towards what's called mechanistic design. Mechanistic design uses stresses and strains, and we've got thousands of test sites of highways across Canada and the United States that we use to calibrate it, but we have very few permeable pavement locations. So we decided we needed to have some mechanistic approach to this, and so the industry got together and sponsored a research project at the University of California, Davis, California, to build full-scale sections of permeable interlocking concrete pavement, and then to load them and to literally put hundreds of thousands of loads on this pavement using an accelerated load tester you see on the left. What it did was it went back and forth, back and forth, back and forth, literally for months. We did it in soak conditions, we did it in dry conditions, and we measured the deformation or the distresses that we saw. And the distresses are typically rutting-based distresses, so that's what you see in the middle there. Extensive technical report. All of that methodology was then incorporated into the ASCE document, and as well as this Permeable Design Pro software. All right, so that's your background. So now we talk about the software itself. And so everything I'm doing here is scripted on slides. I'm not going to show you it live, particularly given the current situation and potential for internet issues and whatnot. So anyway, we're going to talk about the program. When you turn it on, this is your opening screen that you get. You have a choice of doing it in US units and US customary units or SI. Originally, the older version, we allowed you to flip between those two as you went through the program, but basically determined that most people will do one or the other, not typically flipping back and forth in them. So, and then there also were some compatibility issues when we added the ASCE method to it. So we basically are making you decide which one you want at the beginning. So you choose that, and you see the red arrow on the left. Then the methodology used for design. This will allow you to toggle back and forth on these designs if you like to. So you have basically the AASHTO-based structural design method and the ASCE-based structural design methodology. The hydrology all is basically the same. So we'll basically just, the structural design is different one and the other. They produce similar results. The ASCE method is a little less conservative, I would say, based on the findings that we had on this accelerated load testing that was done back in California. So you have a choice of methodologies. The project definition, we need to know something about what you're designing. And so we're going to walk through each of these elements here on the left. We need to know about your geometry of your pavement area. You know, we need to define that. You know, what's its length, what's its width. If you put it in a length and a width, it will calculate for you a area. If you don't, if it's an odd shaped site, you can simply take the area and plug the number in and it will overwrite it. Everything that is white is open boxes looking for an input from you. Everything that is yellow is a completed one. Where it says pavement geometry on the left, if you go and hover your mouse over top of that, it will pop that out and give you some information about it, of what it's looking for. Below that, we have a contributing area description. So in that box, you basically enter what's the area of all the water that's coming from elsewhere, not your permeable pavement, from elsewhere. This could be, in this case, we got a soccer field, we got an asphalt roadway, and it wants to know things about how big is that area, because we have to calculate water volumes. We want to know about its runoff, how much water will go into that surface and how much water will run off. We need to know about roughness coefficients. You select from a box and it will tell you what kind of, is it a field, is it a hard surface, and whatever, and it will give you a number that you can use, or you can enter your own. And then we have information about slopes, how much slope is on the area that comes to my permeable pavement, because that will dictate how fast the water moves. And then we also have the length of overland flow, so an average of where the middle of your roof of your house is, for example. So how long is it going to take to get to the permeable pavement system? In terms of file actions, on the left, we have got file. So file basically talks about new project, setting up a new one, open an existing one, delete a project, some basic housekeeping things, save as, etc., creating AutoCAD drawings. All of the data in the system is basically stored, and you can back up your data. And we'll create a zip file with all your information, and you can store someplace. You can also back up a file or a single project or whatever you wish and send it to somebody else. They can then open it with their system and restore it to their system, and you can be talking about the same thing back and forth. So this facilitates troubleshooting or displaying or other people using your files, which is all able to do that stuff. So it's a very neat, good feature to back your things up. You can store data on your own directories or the system directory it's set up. It's very, very, very easy to do that. So this is what this is. So when you click setup, it has a couple of things. It's got project path, which basically says we're sending it to the default that we as the software designers have chosen for you, or you can put a user selected one and you can save it to a particular project file or a drive on your computer or a thumb drive or whatever you like. And so you can do this back and forth with these elements. The default values, the program has in it a whole series of default things. And so it's saying, for example, on the right-hand side there, the paving and bedding layer thickness in millimeters or in inches. And so you can, if you're using 8-centimeter pavers with a 50 millimeter or 2-inch bedding layer, you put them in here. We've put defaults in for everything for you to use, which are the most commonly used. And if you don't like them and you want something else in there, you can simply go and edit them here. You save it. Or if you screwed something up that you didn't like and you wanted to go back to the original default values, you click on the bottom, it says restore original system values, and it will bring back what we've already provided to you. So you can make your own, you can make it easier for yourself to use it if you use different thicknesses or materials or defaults of layer thicknesses or whatever, coefficients, all that kind of stuff here is easily able to be changed. The analysis button basically allows you to do a few things. One thing we use we call real-time simulation, and there are buttons below I'll point out later to you. But real-time simulation, if you click that on, it means every time you change anything in your design, your project, whatever it is, it will recalculate the results for you. So it's just back and forth. Instead of having to hit a run button all the time, you're changing things. What happens if I made it, 5 inches or 6 inches or 7 inches or whatever? As soon as you change and move the focus away from your input, like tab or arrow down or whatever, it's going to recalculate everything and give you the results real time. So I use this a lot because I do a lot of what ifs and changes and things like that. We have a simulation step time interval. Your choice is to what are we going to display for you? Are you going to display it in 1 hour increments? Are you going to do it down to 6-minute increments? We actually do the calculations in actually 1/10 of that. So they're repeated and then averaged over the time interval to give you whatever you select you're going to use. When you use something like 1 hour, so every hour it's going to give you 12 points on a curve, for example. If you go to 0.1, it's going to do it every 6 minutes. Well, also, as I'll show you later, you're able to get that data out in 6-minute intervals if you wish as well, and you can copy them to spreadsheets. And so it makes for much better curves. It makes for much better understanding of where the water's going from and to and things like that. So you have a choice of that. The simulation model configuration is a little bit different. What it allows you to do is on the right-hand side, it says analysis model configuration. You have 3 choices in there. Basically, you have choice 1 is allow the rain to rain on your pavement for 24 hours and stop. Choice 2 is to allow the rain to go for 24 hours and then continue the modeling because the water that fell on your roof at the end of 24 hours hasn't got to your pavement yet. And so you can do that and say, I want to continue running this model, not for just 24 hours or 1 day, I want to go up to 7 days. And so it will then continue the calculations from the contributing area runoff going to your permeable pavement system. You can also say, well, you know what, keep running this thing up to 7 days until the base saturation, the water in the subbase and base reaches a certain level. So a lot of agencies that do permeable pavement designs require you to have the water removed from the pavement within 72 hours or 3 days. And so what you can do is say, set it up for 3 days, and you can say, keep going and tell me, model for me, when is the base going to empty? It may be 26 hours, it may be 50 hours, it may be 70 hours, whatever. And you can say, well, make it half full, make it 10% of being full, make it 0, whatever you like. And it will continue that modeling on a continuous basis. And I'm missing one, 24 hours, base saturation. I think I got them. That should be good. There is, go ahead, Dave.
No, you covered them.
Okay,
yeah.
Thanks, no problem. So now we've got help system in here. Help is very extensive. If anywhere you are in the program, you hit the F1 key, it will pop up help for that area you are in the program. If you wish to just look at the help menu, you simply go to the help button there, and what it will do is it will give you all of the calculations, all the details. There's nothing hidden. Everything that is being done and how it's calculated. If you're a technical person, you can go in there and you can find out how it's being done. You can see the list here. You can type a keyword. You can print the system, all the details of these things as well. And so everything you ever wanted to know about hydrological and structural design is covered in the help menu. So it's quite extensive as well. So I did talk about the project definition already. I mentioned we need to know the permeable pavement area. We need to know the contributing area coming onto the pavement structure. And you can change this. You can say, well, there's a button in the middle that says runoff from contributing area does not exist. This simply means I'm going to, stop the runoff. So what happens? Only the water that's coming to the pavement is going to be there. Or I can change this. I can add more areas. I can change the area, the size. Typically we usually have 3 or 4 different descriptions or different areas that may be contributing water to the permeable pavement. All that stuff can be changed. When you, on the left-hand side under project definition, you can see there's a whole bunch of things with flags on them. When you first open the program and you haven't done anything, you're going to see a lot of red flags. The flags can be red, yellow, or green. Red means I can't run your program for you because you haven't entered something. And so you go to the red flag and you have to enter something. The yellow means, well, we've got a value here, but maybe it's outside of the typical parameters. You want to come and look at this, and it's a caution thing, but it will allow you to run the program. When it's green, everything runs, obviously. There is a manual run button down there where it says run options. You can select all of the little buttons there. Well, actually, the project definitions, you see little negatives and positives there beside it. You click negative, it's going to collapse them into smaller areas. You click plus, it's going to make all of the layers that are in there are going to come. You can see them all. And there's a green, yellow, left, right button there as well. That means you can step through that and enter the data, one after another, just to walk you through it. And then the time intervals and the alternatives, how you do the calculations, are also highlighted in those buttons beside the left and right green arrows. And so the stuff that's in the main menu at the top, where we looked at analysis, is also a single button. So once you get to use this, you don't want to go and click on the analysis and scroll down and find out what you want. You just go ahead and click the actual button that you have that you want to show. I mentioned the real-time simulation already. So basically, as I said, if you can access it here as well. You click on it, you click on the real-time simulation, it'll put a checkbox beside there, and then everything that you do afterwards is going to rerun the program automatically when you've entered something and changed something. And all the data gets recalculated at that point in time. The analysis results, ultimately, there are tables, charts, reports, grids that you can copy and paste to an Excel file and all of this kind of stuff. We'll talk about them in a little bit more detail later. This last feature on the top here, this beside the design method under ASCE, I use this actually quite a bit. It's a reload the last saved version. So what you're doing is you're doing a design and you've got something you're happy with and you click save. So now I've saved that time stamp basically on that design. Now I'm going to go play with some stuff and change it. What if the area was twice the size? What if I had more contributing areas? What if I changed the methodology of how I do the testing and all that stuff? And you're going through it all and you're not liking what you see. And you go, you know what? I want to go back to what I saved. And so instead of opening the project again and starting over again, you just click on that reload button and basically we'll go back to the last time that you saved it. And so, it became very convenient. So when you're a frequent user of this, it just makes life a little faster and easier to work through. All right, so let's go through a little bit of an example here. And this is this is actually a project that both Dave and I had worked on a while back. And we've got a existing roadway in a city, and the city decided they wanted to do a permeable pavement as a demonstration project. And so they went out and picked 8 different locations, and we went out and looked at those 8 locations and said, guys, none of these are good candidates for permeable pavement. Some of them were because they were detour routes for major truck traffic going through. Some of them had lots of trees that had tons of leaves above them that potentially could clog the permeable pavement. If you're going to do a demonstration project, you really want to make sure that you're going to have a good chance of success. And so eventually we found this road, a different one. And it was a great candidate because we've got sidewalks on the south side of there. The road is called Alston Way. We have the road itself, and they reconstructed the roadway. It was in bad shape. They wanted to reconstruct it anyway, so they thought they'd reconstruct it as a permeable interlocking concrete pavement. So we went through and looked at a whole bunch of things. The age of the utilities that were under there, the utilization of the roadway. Is it a major bus route? Is it a major bicycle route? Is it, all the different things you would look at, and actually came up with a whole criteria. And like good engineers, we develop spreadsheets to help you with the decision making. And so this one was selected for the particular project. Water, where does it come from? Well, it rains out of the sky, obviously. And in this particular case, this is a project near Oregon, Portland, Oregon. And we have asphalt roadways and permeable parking areas. And so what happened is water from the asphalt roadways are going to come and run onto my parking area. So I need to know how much water is there. So back to Alston Way, we have a contributing area. So we looked at the area around it. And so water can come from the adjacent roadways. This one actually has a little bit of a slope on it. It can come from the green part, which was basically the sidewalk area next to a school and some other buildings that were adjacent to the roadway. And a portion of the water from that park came to visit us. And so you can do this from LiDAR, from elevation shots or whatever, and you're trying to determine the area that you're going to be having water going to it. And so they're fairly large. You've got 40,000 square feet in the park area. We've got others coming from the red area from the pavement surface, and then we've got stuff coming from the sidewalks adjacent to the building. And some of that was runoff from the building as well. So all of these areas, we basically build them into our Permeable Design Pro. So pavement length, pavement width, pavement area, obviously calculated. And then we go through each of those, and you can see there we've got contributing area, the sizes of them, and then you select things. So curve number, basically scale is 0 to 100. If it's 100, it means all the water runs off it. In this particular case, we've got concrete sidewalks and we've got park sidewalks as well. They are hard surfaces and the majority of water will run off of them. Not all of it will, but the majority will. So that's why we've got numbers like 98. Grass, when you see grass, when it's green, just because it's grass doesn't mean water is going to get in. If you've got grass sitting on top of 50 millimeters, 2 inches of topsoil, and below that's clay, the majority of water will actually either have to evaporate or it will run off. And so just because it's green doesn't mean it infiltrates. And so you have to be aware of that so you can select that curve number that's appropriate for it. You can see the roughness coefficients are different, the slopes are different, and the distance of flow is different as well. So that's basically the characterization of the contributing area. So now we're going to start the pavement design. So I know what my permeable pavement is. I know what my contributing area is. I know what my rainfall is going to be. And so now I got to talk about what's my pavement structure going to be composed of. And so we start in the project definition on the left, and you go down through that menu. You can see the next thing is subgrade layer. So subgrade layer is basically the ground. So this is what we're going to build our pavement structure on. So we need to know about it. If I build a pavement on something like sand, in this particular case, silty sand is two things that's good for a permeable pavement. One, it's got good strength, so it can build a relatively thin pavement structure to support the traffic. And the other is it has good infiltration capacity. So water will get into that subgrade, this is why you see tons of permeable pavements along rivers and lakes. And I'm near Lake Ontario, so there's what used to be Lake Iroquois was around the area, and there's lots of sand in those areas. You go to Nags Head, you go to coast of Maine, you go to the coast of Oregon, lots of great places for permeable pavements that have sandy subgrades. Advantages are, again, could be thinner because it's got better strength capabilities, and it's also got good infiltration capacity. Where the yellow bar is, where it says SM silty sand, that's a default. And so what the program has is defaults for 8 or 10 different subgrade types. I think it's 8. And so you can select a default and it will populate the basic information from that subgrade. Or you can literally, beside that yellow box, you'll see pluses and a little X and a save button. You can enter your own. So this could be Dave's soil. It's my subgrade. And so I can then go through and I need to enter the gradation, the size of the particles, because the size of the particles of the subgrade define its permeability. And so when we do some calculations based on that, the defaults are there for you to use and they're reasonable. But if you're actually designing and going to build a permeable pavement, it's strongly recommended. In fact, both of the manuals that I showed you earlier will tell you some information about how much testing you should do. In Alston Way, we dug test pits through the road into the ground and did permeability testing of the ground. We want to know what the structural capacity is so we can do testing of those materials. So the defaults are fine. If you're doing a preliminary design, say perfectly fine. But if you're going to do an actual one, you should do actual data. You should actually go get lab data and select your own information for it. The second portion of that subgrade layer is basically the subgrade strength. So again, it populates it with this silty sand here that we just showed you, and then now we've got typical values. And so you can choose the methodology of strength. So what is the basic information for strength of the material? In this case, I've got California bearing ratio, I've got Florida lime rock bearing ratio, and I got R value. Interestingly enough, the CBR, California bearing ratio, was invented in California, and they don't use it. They use an R value mostly. But you can. It's a method. It's a component of the strength of the ground. So all all literally pavement design procedures use what's called resilient modulus. And you can see the resilient modulus there on the screen. And so what it will do is if you put in a CBR or a Florida lime rock value or an R value, it will convert it to resilient modulus and will tell you what that is. If you've seen things like 10 times CBR equals resilient modulus, ignore that because it's actually wrong. The guy that invented this whole thing used to work for me in Vicksburg, Mississippi, and he spent the last couple of years of his career telling people that 10 times CBR is not right. So there's a different calculation that's done here, and if you hit the help menu, it gives you the equation for it. And in fact, it gives you all of the equations for each of these individual values. So you have to select a value. We can also then apply what's called a resilient modulus reduction factor. And so with the AASHTO design in particular, we can say, well, you know what, the subgrade is going to be wet for, 10% of the year or a third of the year or whatever. And so you can actually reduce it by an adjustment factor. So you can say, well, I think it's this number, but really it could be less because it's rainy season here, and so you can adjust it and it will just basically deduct and reduce the strength value and the resilient modulus. And if you do that, you're going to end up with a thicker pavement structure. So it's kind of a safety factor. Then we need information about the material, the soil. So we've got bulk density, specific gravity. Those are the two major things. Specific gravity of rock, for example, is around 2.7, 2.8. What it does is it's calculating porosity. And so it uses the gradation that you entered and its density and information, and it comes back and tells you that I have so much space available in the rock because that's what I need, or the soil, so that's what I need to determine how fast water can move through it. Permeability values are calculated. You can see there in inches per hour or feet per day or in meters per second if you're in the metric system. And so it'll do the calculations for you. If you know what the permeability is, you've done some testing, type it in there and just overwrite the value that's there. Long-term permeability reduction is another safety factor. We assume that you're going to get things washing into your permeable pavement. And if I have something like a sand and I've got a lot of dust or airborne dust and things like that end up in the pavement and get washed to the bottom, it's going to sit at the bottom and it's probably going to reduce the permeability of the soil. So we allow a reduction factor. And so this case, you can say, here's my permeability, but I want to apply a 50% reduction factor. So I'm going to reduce it, which will then mean I have to deal with water someplace else. Okay, now moving on to the granular layers. Basically, the granular layer is defined as the base and the subbase. So we usually build pavements with either one or two layers of aggregates or materials below them. It depends on the traffic, of course. If you have very light traffic, you may only use a base. But as you start getting thicker and thicker base requirements, so if it went from 4 to 6 to 8 to 12 to 16 inches of base, it's probably better off if I used a larger stone subbase, which is going to be cheaper for me to buy, and it's going to be more porosity, so I'm going to be able to store more water. So typically, we recommend 100 millimeters, 4 inches of a granular base, and then everything below becomes a granular subbase. The reason 4 inches or 100 millimeters is chosen is because the base, we want it to be smaller aggregate sizes. We want it to be able to smooth, so we can make it smooth pavement, a permeable surface on our pavement. And the smaller the aggregates get, the lower the permeability gets. And so we don't really want to, and the lower the storage capacity becomes. So that's why we move on to larger bases. So the 100 millimeters, the 4 inches is reasonable for a 1 inch, 25 millimeter size aggregate, typical. And then you go to the larger layers below, they're typically 50, 60, whatever millimeters, so 2.5 inches in size of the aggregates. And you can't lay that down in, 75 millimeter, 3 inch depth because the aggregate's so big. And so we recommend minimums, a minimum of 4 inches, 100 millimeters of base, minimum of 150, 6 inches of subbase. And so we'll talk about that as we move forward a little bit more here too. So you pick this. This is why we have the base thicknesses. You can change this. You can say this is the default that's populated from the default values you saw in the setup menu. It will default to 4 inches or 100 millimeters, and then you can change it. You can say I want to have a base layer only. No, don't calculate a subbase for me. Make it all base. Perfectly good for a low volume parking lot or my driveway, something like that, because I don't need a very thick pavement structure. If you select the subbase layer, it will always give you a minimum 4 inch base. And then it will calculate how thick your subbase needs to be, keeping in mind that it won't go below 6 inches or 150 millimeters. And so your choice. And then we've got a button that says apply choke criteria. Choke criteria is based on the U.S. Army Corps of Engineers. And what it means is when I put one layer of aggregate on top of another and they're different sizes, I want to make sure that the layer I put on top, so the base that I put on top of the subbase, is not so small that the aggregate particles are going to fall in between the holes in the subbase, or that the bedding layer is going to fall into the holes between the base. So when you apply the choke criteria, it goes through and calculates ratios based on your gradation to determine whether or not each of the layers is going to be able to basically lock itself into the layer below it. And so that's the choke criteria. Yeah, and also, I guess I should have mentioned this. When you're using the ASCE design method, you have no choice. You're getting 4 inches of base because that's how the testing was done in California, and how, you know, it's just logical. That's a reasonable thickness of material. That's how the design tables were developed. Then now we move from our base to our sub-base material, and you get to pick what you want. It comes loaded with some defaults. This is ASTM number 2, 3, and 4 stone. This is a gradation that is determined based on standard sieve sizes. If I go to any quarry in whatever Colorado Springs and I ask for ASTM number 2 stone, they probably look at you with a funny look and say, "What?" You know, or if you go to California when we were building this thing in Davis and you say, "I want some ASTM number 2 or 3, they go, "What? That stuff. Yeah, we call that entrance rock." You know, and so, or it's typical to be like things like railway ballast, which is about the same sizes. You don't need to use the defaults. You can enter your own, you can add them to the database, you can put your own gradations in, whatever is local. I don't like going to a different place or location or whatever, a different city, and saying you need to do this. I go find out what do you have that you produce that's reasonable for me to use as an engineer, that's going to get me the properties I want in terms of strength and in terms of permeability, and I'll buy that. That's what I want because it's least expensive because it's already being used for other applications. And so you don't need to have to you don't have to use these materials, so you can actually enter all your own data as well. The bulk density, specific gravity, all that stuff is the same as you saw for the base, so you go through and it will calculate permeability. You can see that this ASTM numbers 2 stone has massive amounts of permeability. You get water in it and you put it on a hill, it's gone. It's just going to go downhill like crazy. So that's good and maybe not so good sometimes. Sometimes I sacrifice permeability and void ratio for strength instead because I've got high traffic and not so much rain. Maybe I'm in Phoenix or something. So, you know, I may do something differently in a place like that than I would if I was in Houston. So again, very, very dynamic. You can do whatever you like with this. As you go through this, now we're talking about, we started at the subgrade, we went to the subbase, we went to the base. Now we're talking the paving layer, the layer on top. So this is our permeable pavers. This is also a bedding layer, a small thickness of about 50 millimeters, 2 inches of stone chips that we place our pavers in when we seat them into that surface. These are not like conventional pavers, all right? These are permeable pavers are purposely designed units that are basically spaced apart a little wider than normal pavers would be, and you do not put sand in there. If you ever see a permeable pavement that says, you know, put this bedding sand down or this joint sand down, it's wrong. You can't do that. You're not going to get water into the system. Water in a permeable pavement system goes in the joints, between the pavers, because the pavers themselves are really hard, durable, very high strength concrete, and you don't get water through them. You get water between them in the joints. And so we don't want sand in our permeable pavement system. So we have a bedding layer. We're defining what that is. Here's your defaults of what they look like. It's smaller particles, 90% or so is 3/8 of an inch or minus there. So it's, you know, they're fairly small. We don't want them to be too big, and we do want a little bit of gradation with them because we want them to fit in the, you know, to be the bedding and to put in the joint material, because we need to have load transfer between the pavers. So we need to have shear capacity. So when a tire drives across one paver onto another, it transfers load from one and it becomes an entire system. So we want to make sure that we have some of these materials there that are suitable for it. Then we go to our paving layer, and this is our surface. And so we combine the pavers and the bedding layer to be one layer. We call it the paving layer. And so that's why it's 5.125 inches here. All pavers come in metric units. They're manufactured by equipment that's all built in metric units. You can have 6 centimeter, 8, 10, 12 centimeter pavers, but this is the US conversion of that. Then there's a thing here called the infiltration rate into the permeable pavement. This is very, very important for you. You could have the best paving system that you ever had, but you've got very little water to be able to get in through the top of the paver. So it's pouring massive storm coming along, and underneath you've got lots of storage capacity, but you can't get the water in the surface, right? So this is very important, and this changes depending on manufacturers, configuration of pavers, the type of bedding or joint material that you have there. And so in this case, a normal permeable pavement will handle 100 inches an hour. There is no storm in North America that's 100 inches an hour. You know, place I keep mentioning Houston because they recently changed their numbers, but you know, you get 14, 16 inches of rain in 24 hours. So all permeable pavements, take a bucket, throw it in the air, it comes down, it's gone. I mean, they're extremely permeable. With time, though, they could reduce their permeability. So you can design this for something substantially less. And so usually we look at these and we say, yeah, it started out at 100 an hour or whatever, and we're going to design it for 10, for 6 inches an hour. 6 inches an hour is still a huge amount of permeability. But you have to be cognizant if you're doing, I'm working with somebody in Texas now on a project for an alleyway where you've got tons of water coming from all the buildings around it, and the ratio of incoming to permeable surface is so different, so huge. I can get the water to the pavement, but the pavement can't get it in at the end of the day. So this is where this comes into play.
Yeah, just to comment on that,
please,
yeah, Dave,
please.
just to comment on the 100 inches per hour. Yeah, most permeable pavements when they're new, or you know, depending on the joint widths and the joining stone, you know, somewhere between 300 and I've seen as high as 800 inches per hour, you know, for brand new installation. Yeah, I think considering that number, you know, 100. I typically put 100 in there, although I had actually had some fun playing with that number and decreasing it and systematically, you know, 10 or 20 inches at a time, running the program and seeing at what point there's water that's just kind of standing around waiting to get in after the design period. And what that indicates is that if you've got contributing drainage area, as Dave described before, not all that water is getting in there. So if a safe approach for that particular number, if you just put 100 in there, you're in good shape. You can, but if you actually know the initial infiltration rate of that permeable interlocking concrete pavement, fine, put it in there. It will definitely be over 100.
And with time, also, I mean, you may get some reduction of the permeability of the surface because you get some
Right.
Materials in there, and you go out and you test this. There's ASTM standards for the tests. You measure the permeability. You can come back to the program and put in the actual and see, is it still good enough to handle the storms that I want it to handle? So it's an iterative process that really works quite well. All right, so now moving on to the hydrology, the rainfall side of things. So again, we're moving down in that menu to the left. Our precipitation. So we want to know what we get. So right now, you've got, I picked Houston. I keep picking on the poor folks in Houston because they've changed things as certainly climate change and Harvey changed the way they do things in Houston. You can select a city in the database, but it's got a bunch of cities, most major ones. Most people don't have to change much because the city's likely there. So you can pick that and it will come back and it will do two things. It will give you the distribution of rainfall that would occur for a particular storm, for one of the storm patterns that's in the database. And so North America has basically 4 different storm types. If you're in the middle of the country, you're going to have a one storm type that basically is like this one, where it starts out raining slowly and then it gets a lot more in the middle and it kind of peters off. If I go to Seattle or I go to Bangor, Maine, I'm going to find a different storm pattern that's going to be more of a continuous kind of rainfall. So we need this to do our calculations for our hydrology. Then if you look at, when I open that up, there's the list of the cities that are in Texas that you can select. You can select the country, Canada, US, and New Zealand currently. You select the state, the province, whatever it is, and it will come up and give you whatever they call them. I forget what they call them in New Zealand. And so it'll give you data on the rainfall, the storm pattern, the daily rainfall that you have. And here it's giving you the amount of rainfall. This number here, you can see a 2-year, a 5-year return period. So this is what's the probability of a certain storm volume or a depth of water coming at a certain time. On the bottom left, you can see add city, and the add city function will allow you to basically put your own city in there and put your own data there. When you do that and you select add city, it's going to say, well, you told me you were in the US and you're in Texas, so what city do you want to add? So here's me adding Waco, Texas. And so you select the storm pattern for Waco. You can get this from the NOAA website. You can get this from Atlas 14 information, wherever you want. And you type in the values there, 3.79, 4.9, et cetera. And on the right-hand side, when I clicked on average daily rainfall, you have a choice of entering 365 numbers. So this is the cumulative distribution of rainfall that happens over the year. That's typical. And so I had the occasion to go in and do this, and well, wow, that's a real pain in the butt. So recently, a couple of weeks ago, we made changes to this, and there's a series of database files of rainfall based on the U.S. long-term, or the U.S. and Canadian long-term pavement performance study. And so we've imported a spreadsheet that has all of the rainfall data, typical average yearly rainfall. And so you can actually go, it will open when it says in the bottom, import daily rainfall, you click on it, it brings up Texas, and instead of having 5, 6, 7, 10 cities for Texas, it's going to give you 50 to 100. And so you can simply go along and click on Waco in this particular case in the bottom right, and that's going to bring me all of the typical rainfall distribution for 365 days, average yearly rainfall distribution. This is current up to now, as of a couple of weeks ago, what was published. As time goes on, these numbers may change. They're long-term averages, so really shouldn't change much. But with global warming and stuff, you may see changes. And so all we would do is update the database, and when you get an update coming to you, you'll end up with the new rainfall statistics. It also shows there's your distribution of rainfall. We'll also show you the distribution of contributing area here. And once you're done, you say, okay, off we go, and we can go do our design stuff. Then what will happen is if you click run, or you use the auto run function, what it will do is it will go through and calculate all the water volumes that you get from rainfall, the volume of rainfall, the contributing area runoff, and the total volume of rainfall, and it plots it on the bottom. The colors in the curves are 2, 5, 10, 25, 50, and 100-year design storms. On the left-hand side at the bottom where it says results, you can just show all the years. You could show 1 year if you wish, all that kind of stuff. And you can include the contributing area or not include the contributing area here. So I can say, well, if I don't have any contributing area, how's my pavement performing? And if I do, how's my pavement performing? And so you can toggle it on and off. You can pick in the storm return period there's a little arrow. You can step down through there and pick one at a time, and it'll show you on the graphics and screen below all the information about rainfall. Comment on rainfall is when you start doing this, I'm amazed. I mean, how many times I shook my head about the volume of water that we get that comes from the sky. It is incredible. And it's huge numbers that we're talking about. I can't believe how much stormwater, comes from a typical storm event over the areas, the surface areas that you have. On the structural design side of things, structural design for AASHTO, it needs some information from you. It needs initial serviceability, terminal serviceability. I'm not going to go into the whole AASHTO design process here, but we give you defaults that are very typical for a permeable pavement, and you do not need to change these. You can if you wish, but you do not need to. So it's your call. These are typical, and basically it's how well do we build it in the beginning, and how far do we let it go before we do some repairs or something on it. And also we need to know about traffic information. Our traffic information basically is on the left-hand side there. You can see you can select a specific type of either roadway or parking area, and so once you pick one of those two, it'll either give you a default value or it will give you some calculation capability to characterize your traffic. On the right-hand side, you can see where it says parking lot traffic. We've already given you the answers in category 1, 2, and 3. And it will change the design traffic in terms of equivalent single axle loads based on that. Or you can do like a typical pavement engineer would do, and you go talk about how many years do you want it to last for, what's its traffic, how much is going in each direction, how many lanes do you have, how many commercial vehicles do you have, and it'll calculate a thing called ESLs through there. ESLs are the equivalent single axle loads for design. We don't design for years, we design for ESLs. A permeable pavement that has more than 600,000 ESLs, the little flag beside it will turn yellow and tell you that's a lot of traffic, guys. If it hits red, if it hits 1 million ESLs, it'll actually shut itself down. So it says, you know what, you get more than 1 million ESLs, go find yourself a decent pavement engineer who's going to be able to design this pavement properly. And I've been involved in lots of heavy vehicle situations. Tanks actually built a permeable pavement to handle M1A1 Abrams main battle tanks. So if you know what you're doing, you can go find yourself somebody who can do the calculations and do the detailed calculations. So we're warning you, just be careful, guys, that kind of thing. In the analysis settings, which is getting down to the bottom now, we have stuff. We have stuff that says, well, click the box in the top, do not allow for runoff, which means that if you're building a permeable pavement, it's like you put a wall around it. And when it rains, all the water is going to go into the pavement, or it's going to start ponding on the pavement in the layers and then on the pavement because you built the wall around the outside. If I click that off, so in other words, you're allowing runoff, when it comes in, water's coming to your pavement, if it can't get in, it's assuming it's going to go off someplace. It's going to find someplace else to go. This may be a supplemental drainage system. It might be a stormwater pond or something like that. Usually, I design them for no runoff because we want to see if we can control all the water. Pavement slope, if you say do not allow for runoff, it just says, I don't care what the slope is. It's not going to come off the pavement, run off the pavement structure. And then I have water level. Water level, this is the current version that if anybody has this, you click on it or you buy it now, you're not going to see that thing that says maximum allowable depth in the granular layer. We've made it so you don't need that anymore. But anyway, you'll see initial depth of water above the subgrade. This means that if we're building our permeable pavement and I'm in Phoenix, and it rains once a month, any water that gets into the ground is going to go into the ground. I mean, it doesn't matter how much you got there. If you get a month of time, water is going to infiltrate into the subgrade. If I'm in Seattle and it rains every afternoon, or Florida, then what I do is I say, you know what? Yesterday is still water got in the pavement structure. It hasn't left yet. And so what I'm going to do is I'm going to compensate and say that water that's in the pavement now can't leave. So I'm going to account for that by saying, it's going to be 2 inches in this case. Below it talks about underdrain pipes. You can use pipes, you don't use pipes. If you go to the manuals, you can look and see the difference between a full infiltration design and a partial infiltration design and a no infiltration design. Not really part of this program here, but you can deal with all this stuff. We need to know how far does the water have to go to get to the pipe once it's in the pavement. We need to know what its diameter is. We need to know its roughness coefficient. We need to know the slope and things like that as well.
Yeah,
so then it goes
let me just interject something here. The beauty of the pipes, introducing the pipes for, say, a partial infiltration design where you're infiltrating some water and then what you can't infiltrate, you drain out. The beauty of the program is you can vary, as it says on the screen, the pipe diameter, the spacing, and certainly the height above the subgrade. And what I've done is typically I've just played around and done sensitivity analysis until I get the right amount of water that I need to capture. It's usually driven by regulations, local, municipal regulations, and it becomes it saves a ton of time from doing hand calculations. You just sort of play around where you want the pipes, and you find out, okay, I'm not overflowing this water into the surface. I'm moving X amount of volume of water out over a given number of hours, and that meets a particular requirement by the municipality. The municipality may say you have to do pre-development, you may have to just capture an inch plus a 2-year or 5-year volume from a 2-year or 5-year storm, and the first inch for pollution, and then beyond that for 5 or 10 year, whatever your storm. So, and that's obviously a specific depth, so that's input early on in the program. So again, it's an incredibly powerful tool to have to do partial infiltration designs.
A lot of what ifs. I spent a lot of time with the pipes. Usually, this and how big they are, how many do you need, what space they need to be, how high they need to be above the subgrade, and things like that. So, lots of this kind of stuff. So then you go in your run analysis, and you see it'll calculate for you the structural capacity. So this is basically saying that I need 5.125 inches of pavers and bedding, I need 4 inches of base, and I need 11 inches of subbase. And so this is the structural design based on that methodology. Then we have the ASCE thickness method, which is a little bit different because this uses, on the bottom left-hand side there, you can see a thing called number of wet days. So in doing the analysis for the workout in California, we looked at how many days of the year would the subgrade be wet, and we've discounted its load capacity based on those days because the strength is not as good as it is when it's dry. So wet clay is caca. It's like toothpaste, and dry clay, you can land a C130 on top of it. So it does the same kind of calculations. And if you buy the ASCE guide, it will give you tables that solve all of this stuff. And this program will basically give you the exact same results that are in the ASCE standard. The results then, you get them out, you get things like rainfall in inches per hour, you get the depth of water in the base dynamically over the time period, over 24 hours. You get pipes on the bottom. You see there's a horizontal line. It means that your pipe drainage started going up and all of a sudden it got full. And so your pipes are running full, so it's dead flat. So that means if your water's going in your pipes and it can't all get in the pipes, then means it's probably getting deeper in your pavement structure and maybe on the surface of your pavement. And so all and the infiltration rate into this subgrade is on the bottom right-hand side. It plots them for you, and it says what storm period is. You had 11 inches on the left-hand side on the vertical axis. We've got a no-go zone that says don't let it get more than 85% full, and then it will go through and tell you what design storm the pavement you designed can handle. If this isn't good enough for you, make a thicker base. Just increase the base, and you're going to see that red line move to the right. You can simply take your pointer and you can move the red line. And so what happens, you grab the red line, you move it to the right, and it's going to tell you what your estimated structural design year storm return period is there on the right-hand side. So it's this is like, when you do your taxes and you're trying to figure out if you've contributed enough to get tax breaks and whatnot on it. So it's really a really decent feature as well. So it recalculates everything in the background. The outputs, in this case, a 100-year design storm, every 0.1 minutes or 0.1 hour rather, it's giving you the data, the rainfall, the volume, the surface runoff, etc. We've added 3 new columns to this, which also looks at the amount of water the maximum amount of water that happens in one of the time intervals. If you selected an hour as a time interval, and it'll tell you what is in there at the end of an hour, but what happens if the maximum inflow happened at 30 minutes? And so we added a couple of columns in the graphic there that will also tell you what the maximum was that came to your pavement structure. We have the ability to click on the little graphic that says DWG on the top, and everything in that design you did, the thickness, the materials, the pipes in, pipes out, geotextile in, geomembrane in or out. You can select geomembrane and prevent any water from getting into the ground in a no infiltration design. It will be reflected in your drawing. And so you can use that drawing, you can change stuff on it, you can recreate it, spit it out in a PDF, spit it out in a DWG file that you can read with AutoCAD, for example. So basically all of those options are there. All the graphics, right click on the graphic, it'll say copy to clipboard, copy paste it in your spreadsheet or in your technical report or whatever you like. And so all of these things are all available to you very, very simply there. And that's just showing you there. Copy one graph, copy the group of graphs, and so you can remove them and put them into your own reports if you wish. There's reports, stock reports, telling you, is it the AASHTO method or ASCE method that you used? All of the basic information about the elements in their permeable pavement are described in great detail, along with some other charts that tell you, is your pavement going to get full for a 2-year storm or a 5-year storm or a 20-year storm, 5-year storm, et cetera. And so again, I'm just showing you on the right-hand side there, if you're exceeding your storage capacity and water is going to be on the top of the pavement later. So it's giving you a simple chart to help you with that. Export to Excel, export to Word, export to PDF, whatever you like, basically. I've explained this already, actually, with the storage goal and in the storage capacity. When that line goes over top of the 15 inches in this particular case, it means it's exceeded your storage capacity and water's going to be sitting on the pavement structure.
Yeah, the reason, just real quick, the reason why we put that 85% in, that's a value you can change in the program, but it's defaulted 85% because we're assuming that there's probably water that may be in that subbase from the previous rainstorm. Yeah, see, we're modeling one rainstorm at a time, and so we're assuming that worst case that the previous rainstorm wasn't far behind the one you're modeling. Now, what I've actually done with this program is I've actually modeled a sequence of rainstorms with X amount of inches of water remaining. I would do the first one, see what's remaining, put that in as the next, store that, do the next, just to see what the total worst case scenario would be if there was back-to-back rainstorms.
Yeah, and I've done that actually with like an alleyway where I divided it into 3 or 4 different compartments, and I've said the first one's going to get this much, what's going to the next, what's going to the next, what's going to the next.
Right.
Exactly the same way.
Mm-hmm.
Graphs, everything is there, copy and paste, all of the different elements that you have in the program, different storm types. You pick one, it will just give you a one, if it's a 2-year storm, it'll just show you a 2-year storm. Everything is available for you to change, to modify, to copy out and place in a report or an Excel file and things like that. So very, very, it's intended to be very simple. It's not high complexity modeling. It's not, some of these programs that are out there are much more comprehensive than this particular one is, but this is sufficient to give you a really good permeable pavement design. So summarizing, so I'm hitting my time here, is that ultimately this is a simple, easy program developed by the industry to help people to design both structurally and hydrologically a permeable pavement system. As I mentioned, if you've got a very unusual case with a lot of different traffic or different complexities of storms, find yourself a pavement or a stormwater engineer that can help with that situation. No black boxes, everything's in the help menus, all the calculations are there. If you don't like what's calculated, you can get the data and you can go and copy and paste it in a spreadsheet and do your own stuff if you wanted to. As Dave mentioned, the what if scenarios are amazing. We sit back and forth with people and, in Skype and whatnot, and changing alternatives. And what if we did this? And what if we did this? And I've got 4 of these projects on the go right now in Ottawa and Quebec City. And all of the stuff, the reports, you can copy and paste them. You can do them in your own format if you don't like the format that we provided in. So with that, I'm going to pass it on. I haven't seen any questions. I'm not sure, Michael, if you have. I know we're at our time limit, but I'll hand it back to you to kind of finish up here, or if there's questions that you want to have. Here's where you get it at PICP, interlocking PICP. Oh, geez. Anyway, sorry. This is where you get it from ICPI, and you can purchase it, download it, and then also the updates that are done to this as we move along. Some people have come up with different features that they thought were awesome that we put into it. When you click on the program, it goes and finds out if an update has been released. If it has, it's going to ask you if you want to download it. Right. So I will, Michael, do we have any questions or time for them?
We got a moment. We do have one question. If anybody does have a question after the event, you can email educate@icpi.org, and I'll make sure that Dave Hein gets them. But real quick, Dave, is there widespread use of this program in design companies and/or municipalities?
There's more than 5,000 copies of this out there being used. How extensive they're being used, I'm not 100% sure of, but there are lots of them out there. It is. I always get questioned on this too. Actually, is this something that's very commonly used? And my answer, of course, is yes. And it's very simple to do, and it's easy to explain to people. So again, if I have a highly complex project, I'm still using this to design it. I know what I'm doing. That's why I do that. But if I have, I may do some more. But for 99% of the projects you have, this is more than adequate. Certainly, structural design validated. The California Davis work that was done, and Dave Smith spent a lot of time out there making sure we had decent data from that. It's trustworthy. It's good. Structural capacity is not an issue. So yeah, I mean, it certainly is out there. There's lots of people using. Lots of people have downloaded it again.
See, part of the situation is the hydraulic modeling is based on a rainstorm. It's not. There's lots of hydraulic models. I would say at least 3 or 4 good ones that do continuous modeling. Essentially, look at rainfall over an entire year, passing through basically modeling hydrographs from a year's worth of rainstorms. Those are out there. I know EPA Stormwater Management Model has it. There are others. I think Windslam does as well. That's fine. You will probably, if you use those models and model permeable pavement, you will probably end up with a little more efficient, a little thinner cross section. However, those models do not do structural design. And like Dave said at the beginning, you model the hydrologic side of that nice flow chart, and then you do the structural design, and you end up typically picking the thicker of the bases. And so the strength of this program is that you get not just one, you get 2 different, slightly different design methods for calculating the structure to hold up the traffic. Also, Dave, you alluded to this. I just want to make a real quick comment on the ASCE method. If you actually get into the weeds and do the calcs and compare the AASHTO to ASCE, ASCE will give you a little thinner. It's usually 4 to 6 inches, which is actually substantial particularly if you're doing a big project in cost savings. But it will give you thinner cross sections if you are working in high infiltration soils, or the number of days per year there's water in the base is fairly low. So it essentially favors, it gives you very efficient cross sections, and it favors sandy soils, high infiltration soils, and also semi-arid designs in semi-arid climates where you don't have a lot of days per year there's water standing in the subbase. Just a footnote. So you can save bunches of money by using PICP and using the ASCE method, particularly in those situations.
Excellent. Any other questions, Mike?
Hey, do you know the cost of the program?
I really should, but I don't.
I think it's $95.
Yeah,
I'm glad you brought that up, Mike. You can get it for free, but here's the trick. Okay, the way you get it for free is, first of all, you are a design professional, meaning probably a civil engineer, maybe a landscape architect, and you ask for it through one of our members. Our members will give you, they'll come to us and they'll ask for a code, basically, that enables a free download. Also, when you download it, I believe it's available for 2 computers. So, sort of as a
yes,
backup.
it is definitely available for 2 computers, correct?
Okay, good. So yeah, it can be had for free if you're a designer, but you work through our members. Also, you can contact ICPI directly if you're a designer too. We'd be glad to send you a code. If you got a project that you'd like to do some analysis, we'll get it to you for free. We'll get you that passcode.
So we do have a webinar coming up at the end of May. It's going to be in regard to slabs and planks. Brian Hoare, ICPI's Manager of Technical Development and Market Promotion, will be presenting. You can always visit our webinars page at educate.icpi.org/webinars for more details. And ICPI recommends that individuals and companies contracting for a paver installation job use a contractor who employs at least one person who holds a current ICPI concrete paver installer certification. This ICPI certification demonstrates that the installer understands industry-approved construction techniques and meets specific installation experience criteria. In addition to the ICPI certification, ICPI also offers 3 installer specialist designations: residential specialist, commercial specialist, and PICP specialist. The residential and commercial specialist courses are available online. Again, if anybody does have a question on the call, please email educate@icpi.org, and we'll go ahead and get those over to Dave Hein and David Smith. Dave Hein, David Smith, we appreciate you guys for joining us and presenting this great topic. And everybody on the call, I appreciate you for joining us. I hope that you all have a wonderful rest of your week.